Winner out here. I'd like to thank the organizers for inviting me to speak. Really want to thank everybody for their hospitality. It's been a great week. We've been here since, since Monday. What I would like to do is talk a little bit about our work on, or entirely on our work on CADASIL mouse model, work with Andrew Tell. I'll give you a little bit of background. I think I have the advantage that everybody's presented all the background already, so I don't have to so very much in terms of background. This is Vermont, where I'm from. It's very close to Quebec, and that's the big city of Burlington. You've heard about this today from Costantino and others. We are primarily interested over the years in the cerebral circulation, ion channels, and ion channel control of the cerebral circulation. And about over, I would say 15 years ago, we started looking at vessels not only on the surface of the brain, but in the brain. And we're interested in two primary areas, autoregulation and neurovascular coupling, which you've heard quite a bit about today. And I'd like to provide some evidence for how CADASIL impacts autoregulation and some tantalizing evidence of how it affects neurovascular coupling. You've heard this is a classic review. I thought I was going to change the title of it to yours, Costantino. But this is to illustrate that we're now focusing on brains, small vessels, and arterioles within the brain. They're encased by astrocytic processes, you see here, that ultimately go to the capillaries or capillaries down here. And so I'll describe a lot of work looking at isolated parenchymal arterioles from within the brain, the mouse brain, from controls and CADASIL mice, and then some work on brain slices and looking at neurovascular coupling. And this just illustrates the various elements, the endothelium, smooth muscle, pericyte, which we heard about, neurons, and the astrocytic processes that encase the arterioles. Now, I'd like this highlights our Foundation Leduc Trans Network for small vessel disease, which just started. We just had a meeting this week. What I think is interesting about this meeting, every one of our network members has spoken, or a representative from their lab has spoken over the last 2 days. And our initiation, this leap started with Anne. She contacted me several years ago. She came to Burlington, and I want to show you some interesting give a little anecdotes about how we've come to some of the same conclusions about what CADASIL might be doing on the arterioles and in the brain based on completely different measurements. And I hope you'll find it tantalizing and somewhat revealing. Anne went through this yesterday, so I won't explain as actually a number of speakers did, the mutations, Notch3 mutations in CADASIL on the smooth muscle cells. She sent her mice from Paris to Burlington, and they seem to behave the same in Burlington as they do in Paris. Maybe it's the proximity to Quebec, I'm not sure. Or maybe Fabrice in my lab, who's French, who speaks to them in French all the time. So we are using the model that Anne developed and published in the Journal of Clinical Investigation a few years ago, the R169C, which seems to recapitulate a number of the salient features, pathological features, and functional features of CADASIL. This is, you saw from Anne yesterday, some of her measurements, that there's a decrease in neurovascular coupling, which we're now starting to investigate at the cellular level. And as she spoke about, a decrease in pressure-induced constrictions in peel arteries with at higher pressures, or actually physiological pressures, the constriction reduced by about 30% or so in the peel arteries. So this is the surface arteries. I'll show you data in a minute of looking at the parenchymal arterioles within the cortex, and we went to look at this feature, the pressure-induced constrictions or myogenic tone, which is thought to be an important contributor to autoregulation. So you can imagine as pressure goes up, the arterioles and arteries constrict to maintain constant flow, which you just heard about. If this doesn't happen properly, you can have too much flow or too little flow. So now we dive into the brain. This shows just an isolated middle cerebral artery and a penetrating parenchymal arteriole isolated from a mouse brain, and it's been stained in red for aquaporin 4, which shows a really interesting feature of this, which hopefully Ann and I are going to exploit, or she's exploiting already, that the astrocytic end feet, the processes pinch off, they come off when you take the vessel out. So it will provide an opportunity for us to interrogate what is going on at the membrane of the end foot, the notch 3 in the smooth muscle, and the gum, the material in between. And this is really a sort of now routine, but a tour de force. These are isolated parenchymal arterioles about 500 microns into the cortex before they become capillaries. And you can see this just illustrates the arteriole. We can measure diameter and also membrane potential of the smooth muscle cells with microelectrodes. We can also dissociate cells from these arterioles and look at ion channels directly. So this then shows, I want people, I mean, this is pretty phenomenal. This is where you have job, I shouldn't tell us to Fabrice in front of him, where you have job security because he actually can take out and cannulate 20 micron diameter arterioles from mouse brain. And what you can clearly see here, here's the notch 3 at the bottom, the notch 3 mutant, the catacil mutant mouse in red. As pressure goes up, you can see the arteriole constricts and gets smaller. In control, the transgene, and in the catacil mouse, the arteriole does not constrict as much. So you can see it clearly here, just like Ann presented for the PL arteries. At 40 millimeters of mercury, which is a pressure appropriate for these arterioles, the constriction is reduced by about 38%. So this is telling you something really fundamental. In this mouse model for catacil, at low pressure, the arteries more or less are behaving the same. As pressure goes up, the normal arteries will develop more tone, they will constrict more, but the catacil arterioles don't. So it's a pressure-dependent change in their properties. It's something that's engaged as intravascular pressure goes up. And now if you just put yourself into the blood vessel, think about it. As blood pressure rises, these arteries will not constrict as much and it will affect autoregulation. So the question was, for us, was what's going on here? And so we started to explore that, but we also, because this was a question brought up yesterday, so I put this in, we've also done parallel studies looking at systemic arteries. And here's a big question for small vessel disease. Why the brain? You heard yesterday that skin biopsies are used to determine, to do the genetics, to look at gum, to look to make sure that you have the mutations in notch 3. But what is special about the brain? So we started to look at this, and this is just maybe for later discussion. This shows mesenteric arteries from the same animals. Everything we look at the mesenteric artery from a catacil mouse looks the same as a control. The difference is in the brain. So, you know, I don't have the answer for it, but certainly I think these sort of comparative type studies, and ultimately maybe getting human arteries, systemic arteries, of course, because as I said, nobody in my lab so far wanted to donate any of their cerebral arteries to me. Although I had promised to patch up their brains afterwards. But so there's something interesting going on, and so we're also exploring this. But to get back to the issue of what could possibly be going on in the catacil mice, the arterioles, and the PL arteries where they don't constrict as much to pressure. At low pressures, they do have tone, and the diameter is the same. Everything's the same. So it's something that's engaged by pressure. And this gives you a bit of an overview of things we and others have worked on over the years. Pressure, intravascular pressure goes up. It causes the membrane potential to depolarize, likely by opening TRPM4 and TRPC6 channels. And Albert in the back can tell you all about that. This then opens voltage-gated calcium channels, much like you heard in parasites in the last hour. Calcium comes in, the arteries constrict. Okay, well, so as pressure goes up, you have to have negative feedback elements to put a brake on the depolarization. And there are a bunch of them. There are the calcium-sensitive potassium channels in the smooth muscle, the so-called BK channel. inward rectifier potassium channels that can also hyperpolarize. The endothelium through nitric oxide and endothelial potassium, calcium-sensitive potassium channels can also put a brake. The other one are voltage-dependent potassium channels. And I'm just going to say right up front, we've looked at each one of these elements in the CADASIL mouse model, and the only one that's changed is the voltage-dependent potassium channel. And it's upregulated. The brake is turned on. So the brake's turned on, the arteries, as pressure goes up, wouldn't it depolarize as much, and they would stay more dilated. And I'll just get a couple examples of things that are unchanged. If we looked at the relationship between potassium, external potassium, and diameter, the red's the CADASIL mouse, they're all the same. This is a non-transgene, transgene control, and the CADASIL mouse is always in red. But if you look at dilation to potassium, as you raise potassium, it dilates and constricts. At higher potassium, everything is the same. This tells you immediately something very simple. The inward rectifier potassium channel that underlies this dilation is unaffected. Voltage-dependent calcium channels are probably unaffected because every one of these points are the same. And the calcium sensitivity of vasoconstriction is probably unaffected. So this looks all more or less unaffected. But if, as I said before, if pressure depolarizes and if the brake is turned up, as you go to higher pressures, like 40 millimeters of mercury, that should depolarize less, be more hyperpolarized. And this is what the measurements from Fabrice show, that at 10 millimeters of mercury, remember everything's the same in terms of diameter, the membrane potential is the same. As you increase pressure, which has been well established, the membrane potential depolarizes, in this case from about minus 52 to minus 35 millivolts, shown here. But the CADASIL, arterial or smooth muscle, don't depolarize as much. They're 9 millivolts more hyperpolarized. Less depolarization, less constriction. You have turned a dynamic element. The negative feedback control of membrane potential has been altered. The gain has been altered. And this should fundamentally affect the dynamics of the blood vessel. So this is consistent with a change in electrical properties. And just to illustrate this, this shows a relationship between membrane potential and diameter of a peel artery that we made a number of years ago. And this simply shows the steep relationship between membrane potential of the smooth muscle cell and diameter. At minus 60 millivolts, arteries are maximally dilated. Minus 20 millivolts, maximally constricted. The range where all blood vessels live is in this range, minus 40, minus to 50. Huge changes. This is a control. This is CADASIL, 9 millivolts. And just for the peel artery, this would correspond to about a 30% increase in diameter. So anytime you think about blood flow changing, the membrane potential of the smooth muscle cell is a major controller of it. And small changes and changes in how it's dynamically regulated could affect blood vessel function. So as I mentioned, we tried all the things to look like the inward rectifier looked more or less the same, voltage-dependent calcium channels. We also put on NOS inhibitors, SK inhibitors. Everything we looked at was unaffected, but the membrane potential was different. The only thing left standing was the voltage-dependent potassium channel, which is KV1.5, which you heard about from Ann. And so this is remarkable. I can remember Ann coming over for our retreat, sitting in my office, and based on completely different molecular evidence that the Notch3 gene could regulate the expression of KV1.5, was thinking about the KV1.5 channel. And I said, well, I think it's the KV1.5 channel. And she said, well, how do you know? Or maybe she said it first. Completely different approaches, which actually gave us some sort of a good, warm feeling that maybe we're onto something. And this is just some functional evidence for it. This is a rather non-selective blocker of KV channels, 4-aminopyridine. And what this shows simply is the CADASIL mouse, if the channel is upregulated, a blocker might have a greater effect. And what you can clearly see, 1 in 5 millimolar 4-AP downward constriction causes a much bigger constriction in the CADASIL, consistent with the channel being upregulated, so when you block it, you have a bigger effect. But really, the proof of this is then also not excluding things, and the membrane potential clearly indicates that it's an ion channel, and the 9 millivolt hyperpolarization can entirely explain the difference in tone. we went to then just to do it directly. We isolated smooth muscle cells from cadocyl arterioles. Using the patch clamp technique, we measured potassium currents in the freshly isolated cells. And this throws it. I know, only probably a few people here would like to look at ion current measurements. But if you looked at enough of them, you learn to love them. And you realize you're missing out if you haven't looked at any of them. But the simple thing, again in red, the cadocyl mouse, upward deflections are the potassium currents. Up, the bigger it is, the bigger the current. And what you can see here is that in the cadocyl mouse model, the voltage-dependent potassium current is almost twofold greater. If you analyze this all, it's consistent with a doubling of the channel number in the cell membrane. The properties are unchanged, and we have previously shown that this is made up of Kv 1.2 and Kv 1.5 channels. So it suggests that the channels are upregulated. And so to summarize this, what I've shown is that pressure-induced constrictions are unaltered at low pressure, but decreased at higher pressures. There's a decreased tone in cadocyl. The implication is the pressure-dependent mechanisms are altered in cadocyl, and contractile function is preserved in the sense of the contractile proteins. The parenchymal arterial smooth muscle is more hyperpolarized, and this looks like it's due to an upregulation of a break-on constriction, the voltage-dependent potassium channel, shown here. So this is fine, but how does this? Let's take it the next step. How is this happening? And we had some more clues from work by George Wellman in our department and Masayo Koide, who's in the audience, and they were looking at a completely different pathology, subarachnoid hemorrhage. And this gets to, even though these are basic studies, it gets to the whole discussions we had yesterday, the relationship between cerebral vascular disorders. And so they have a model, and I won't go through. Here's Masayo. She can tell you the details. She's in the back there. By injecting autologous blood onto the brain, waiting now they do a time, but 4 days, and looking at cerebral vascular function. Well, there's been a growing appreciation, and I don't have to tell this audience, that a lot of cerebral disorders are not just big arteries, but it's the microcirculation. And I think in the world of subarachnoid hemorrhage, and I don't think anybody will agree, that there's more and more emphasis on the microcirculation, and as Constantino said, probably contributing to cognitive decline following subarachnoid hemorrhage. But the remarkable thing is that they found in their model that the arteries, both the parenchymal arterioles and the peel arteries, were more constricted at a given pressure. Just the opposite of what we saw. We see them more relaxed. And to make a long story short, because it's their data, they found that there was a decrease in the surface expression of Kv 1.5 channels. And they provided evidence that oxyhemoglobin, through metalloprotease, through heparin-binding epidermal growth factor, can lead to a increased endocytosis and decreased surface expression of Kv 1.5 channel. Now you see where I'm going? Do you remember Anne's yesterday? She'll come back. One of the things in the gum, TIMP3, an inhibitor of metalloproteases. And if that's increased, it would do just the opposite, increase the level of Kv 1.5 channels. So I want to provide some, and this just shows the Masayo and George's data showing that HB-EGF decreases the current density of Kv channels. So we have a different pathological situation, okay, a model, subarachnoid blood, both in the peel arteries and in the parenchymal arterioles, decreasing the surface expression of the same channels that we see an increase in. Now, keep in mind, in terms of blood flow, you turn the gain up, you turn it down, both are not good. So, but this provided some insight, and this is when, again, like Anne came at this from a completely different angle, looking what was in the gum about possible roles of inhibitors of metalloproteases. So we took this one step for sort of a parallel to Anne's study. We said, if we have increased expression of Kv 1.5 channels, then we could sort of simulate what what Masayo and George did, give HBEGF, decrease expression, return it to normal, and could we restore tone? And this experiment Fabrice did. He gave HBEGF to the arteries, looked at the increase in constriction, tone to pressure, cadocyl mouse, HBEGF rescued the tone. So bringing this is also food for thought later on. Completely, this is what this collaboration and the network has been fantastic, other than Anne's fantastic, because all of a sudden we're at the right time and moment for all these techniques to come together to provide major insights. So this could, with an increase of TIMP3 inhibiting metalloprotease, you could lead to a decreased endocytosis of KV channels, and this could explain our increase in expression and decreased myogenic tone. And in fact, this shows Anne's experiment from yesterday. The tone has been rescued by both HBEGF and genetic reduction of TIMP3. So whether this could be therapeutics, but this also gives a very fundamental question we'll talk about later on. How early do these cerebral vascular defects occur, and what is their relationship to the overall long-term pathology of CADASIL? And I think, as Anne said, certainly 2 months are happening in the animals, so relatively young. So the last thing, very briefly, I want to show you what we think, some observation, very preliminary ones, but this is the point of the meeting, of what's happening in neurovascular coupling at the arterioles. Obviously, the Notch3 and extracellular domain and the accumulation of proteins happens at the smooth muscle cells, perivascular space above the smooth muscle cells and the smooth muscle membrane. And these cells are in close proximity to the astrocytic end feet. So we did some preliminary experiments looking at what the effect of CADASIL is on both neurovascular coupling measured in brain slices and calcium signals in the astrocytic end foot, which are controlling the responses. And this simply shows illustration from Anne of some gum deposits between the end foot and the smooth muscle. Very briefly, we make brain slices, cortical brain slices. We preconstrict the arterioles to simulate tone, and we look at neurovascular coupling. We load the slices with a calcium indicator, flow 4. We measure diameter with DICIR and a 2-photon microscope, and we can stimulate the neurons by electrical field stimulation or directly uncaging calcium. And this simply shows an example of an arterial electrical field stimulation. You see calcium goes up in the end foot. You can see the smooth muscle cell layer and the red blood cells, and the arterial dilates. So this would be the sort of brain slice, perhaps equivalent of what Anne showed from the whisker stimulation. Stimulate the neurons, arterioles dilate. In the Notch3 mutant mice, the CADASIL mice, the dilation is greatly blunted, suggesting that even at this level, neurovascular coupling is compromised. But the other interesting thing is when we look at calcium in the end foot, this shows electrical field stimulation, calcium going up in the end foot of the astrocyte. This is the wild type, the CADASIL. You can see the peak calcium is decreased as well as the duration of the signal. This would also decrease neurovascular coupling, potentially. And this suggests, again, very preliminary, this suggests this decrease, the decay of calcium is much faster in the CADASIL mice here. And one explanation for this is that the calcium uptake processes within the end foot have been changed in CADASIL. And I think for us, we have to think about the CADASIL not just being the smooth muscle cell, but the cell that's immediately in contact with the astrocytic end foot, suggesting some fundamental changes. So sort of take-home messages. An early consequence of CADASIL, Notch3 mutation, may be upregulation of KV channel expression and activity leading to compromised autoregulation. How this plays into the overall pathology, I don't know. Obviously, correcting the defect will be a way to look at that. Elevation of metalloprotease inhibitor TIMP3 in the gum leads to an increase in, this is just speculation, surface expression of KV channels based on all the convergence of data. Pharmacological activation of the EGFR receptor and or genetic reduction of TIM3 restores subarterial reactivity. Decreased myogenic tone alone would also decrease vasodilator capacity and thereby alter neurovascular coupling. But also, CADASIL, at least this particular mutation, seems to alter neurovascular coupling and acidic end-foot calcium, and this may play a role as well. So I hope I've planted in you a bunch of things we can talk about later, and also really want to thank everybody, acknowledge our funding sources, particularly the Foundation Leduc, which has made all this fantastic work possible and opened up a new world to me and to a number of our young investigators. I'll show you a little view from our lab window. This is Vermont here. There's Fabrice, who's leading the CADASIL charge in Vermont, our resident Frenchman. Actually, he's drinking wine in Germany. He should be drinking beer. Adrian Bonif, who does everything. This work was done with Crystal Krongard, who's a postdoc in the lab. Here's the gang from Vermont that's in the back here: Albert, Masayo, Gros, and Fabrice. Great collaboration with Andrew Tell. This Carmen, her lab has been involved in a number of the measurements, and also picked me up at the airport by taxi. I have to, this is Anne, at her first visit to Vermont here. She's smiling. You can't tell, but she is. Right there. And this is the Trapp Family Lodge. Anybody knows the sound of music? And I want to thank everybody. Thank you very much.